So if in the snark or graph of 4 chromatic index 4 we have 3 edge cut, yes, then we can cut it and have left graft with these 3 edges. With these 3 edges, out of these 3 edges we make this vertex with this part, and then out of this with the 3 edges we make another 3 part. And then we have a claim that this big graph has chromatic index 4 if and only if at least one of these graph has chromatic index 4. Okay? We are not going to prove this. We can prove it like an exercise afterwards if you want. Some of you can try to prove it. I didn't include this in the exercises, but you can write it down like this proposition. Yes? It's very simple. You don't have to write the text. You can just say, okay, we have this in the snark. We can reduce one of these must be snark. Yes, so you should try to prove it that later. Okay, this is one thing. And then we say snark acyclically for edge connected graphs. And then we have a proposition 12, this claim, Petersen graph is the smallest snark. That will be one of the exercises. I think this is very, very nice exercise to know, to prove that the Petersen graph is smaller snark, yes. We have the proof, you know. Now, up to 175, you was not born yet, yes, but your parents were probably, yes. So there were only 5 snarks. It was not clear if there are infinitely many, or how many. There are only 5 snarks, and the first snark was, of course, Petersen graph, because we excluded these bridges and so on. We don't care. The second 2. So Petersen graph is on 10 vertices. Somebody call me, I don't know how I switch off this. Okay. The second 2 snarks were found out by Blanisher, this Croatian guy who discussed Blanisher lemma. He was working on these things, yes. He found 2 snarks, yes. Then was Sekere snark, some Hungarian guy of 50 vertices. And then Descartes snark, Descartes. This was kind of probably acronym or how it's called it, of Tat, William Tat. Do you know the name Tat? William Tat, he was very good graph theorist, pioneer. This is probably William or Bill Tat. This is his name, yes. Okay. But he published under name Descartes, yes. If I'm correct, yes. So let's see these snarks. Yes. This is the Brownish snarks. They have 18 vertices. You can observe something. You can observe something that here is a kind of a Petersen graph, yes, and here is another one, and they are connected somehow. Yes, you agree. Also here down, Petersen graph. Some edges of these Petersen graphs are removed or halved it. Then another copy of Petersen graph. Here also some edges are cut, and then it's rewired somehow, yeah? That will be your homework to do it. I will give you the operation. So, this operation is called dot product. And now let's go first the other. Sekere snark. This is a Sekere snark. Okay. Then it's kind of 50 vertices or something like that. Descartes snark. How to construct that one? Yeah? Descartes snark. Okay. Isaac. This is the name of some mathematician. He came out with two construction. And then he made two infinite classes of snarks. The first one is with dot product. Dot product. What's mean dot product? Here we have one graph. And here we have another graph. In the first graph, we choose two adjacent vertices, x and y, and we remove these two vertices. In the second, maybe I can enlarge this here, yes? This is the dot product. In the second, you choose two non-adjacent edges, A, B, and C, D. You remove the edges, but not the vertices. You look here, we remove this edge, we remove this edge. We don't have it anymore, okay? Okay? And here, you remove the vertices. Here you remove also the vertices and the edge, and then this part disappear. You see, we have only this, yes? I know. And then you connect them. Then you connect them, okay? You can do maybe another way, maybe this part with that one, so it doesn't matter, yes? Okay? This is officially here is defined with these words. Remove adjacent vertices x and y. This is in the left part. Remove adjacent vertices in where the neighbors of x are s, y, and y. Or maybe I have even okay, to u x, yes. Remove any two independent edges A and B and C, D on the right side, and connect L with I, S with B, and so on, yes. So remove these two vertices, and within that all these edges, remove these two edges and connect it. And this is called L dot R. This is the dot product. So we have the L and R, and we make a new graph. Now, what holds for this one? What we don't have much time now because we have exercising, but we can also prove this if you wish, this part, yes. As an exercise, we can prove this, yes. If L and R are FOH chromatic, so if L and R are snarks, or cubic graphs with chromatic, then R multiply R is also FOH chromatic. So Blanusha found these two graphs, but when Isaac found this construction, it's possible with this construction to construct both Blanusha snarks. Okay? So, but what is the requirement here? You have two snarks, and then make a new snark. Just okay. This should not be difficult to be proven, yes. You can try this exercise, yes. And then Isaac find another infinite class of snarks. I cannot understand how he managed to find them, yes. So it's very interesting, like, because we get kind of flower. Yeah. You can distribute to some people, yes. I don't need it. So this set of problems has also some appendix with these drawings, illustrated flower snarks, illustrated dot product. So it's hard to print it for everybody. Yeah, it's a lot. Yeah. So, But we can send them by email, yes, and so on. Or I don't know how to send them. How to send them this? Do you have email for everybody?
Yeah, that will be, yeah.
So also my slides, I can send to you all my slides if you want. So I have the PDF, but I don't know how to send to you. Somebody send me mail, I send you back. Okay, you Skrikovsky, my mail is skrikovsky@gmail.com. So send me email, I send you then my slides for the first day, my slides for the second day, exercise, this one. Dina has for the first day exercise. And then when for tomorrow I will send when we are tomorrow done and so on. So as we are to literature, for this part, for today part, when I was young like you, yes, I was studying from this book, Edge Colorings of Graphs, Fiorini Wilson. Of graphs, Fiorini Wilson. Fiorini. I like it very much. And then another book which I didn't took with me because I was already too heavy, yes, is the Petersen graph. Book called the Petersen graph. If you look on Amazon, look for the book, the Petersen graph. And here is a chapter about snarks. Here is not, but in the Petersen graph book. We have a very nice chapter for the snarks. And here you have everything else. In the Petersen graph, you have also a very chapter about planar graphs and so on. I recommend it, yes, for beginning to read it. So I'm sorry I didn't took that book because I was too heavy, already overweighted. Okay. I will not spend too much time with this formal definition of what is snark, flower snark, but I would rather show the illustration, yes. He took this part, a claw, yes, and then he connect here into the cycle, and this go like this, then this go like this go like this go like this, oops, yeah, and so on, okay. The precise definition is here, yes. You will get it in the slides and so on. And here are the first three graphs. This is officially not a snark because we have three cycle, but otherwise it's for each color, chromatic index 4. And if you contract this three cycle, what do you think we're gonna get? What we're gonna get here if we contract this three cycle? Anybody can guess? So we into a vertex, and this vertex, because it's triangle, we go. What do you think it's gonna be? Petersen graph. You're gonna get Petersen graph, yes. This one is F5, and this one is F7, yes. We don't have much time to go so much into details, but you know, here is a little bit differently. This is connected, yes. This part is because by definition, by module or something, you get this part is a little bit different, yes. And of course, here a theorem is, this is even theorem, that these graphs are snarks, yes. I give it these two exercise for you, yes. You know, it's not expected that you will solve all the exercises. Then they are not good. If you solve half of them, then you are very good. So sometimes in the exercise may be some problem which nobody can solve it in the world, yes. That's a good exercise. Some easy and some very difficult. Okay, so this is doable, but this is not easy, yes. Okay, so don't be disappointed if, oh, this is too difficult. You have to work more, harder, and you will solve it. I don't know if I have time. I like to speak some superposition. Can I speak a little superposition? This is the last state of art. Superposition. I will go very fastly. Just the idea. This is the more general construction. Actually, it depends how you say the things. I will go very fastly to the slide, but the main idea is like this. The main idea is like this. The main idea is like this. You see that this is like these vertices. This looks like Petersen graph. Yeah? The main idea is to replace the vertices of Petersen graph with some other gadgets, how you call it, yes? And also the edges with some gadgets. And so you actually explode it. Every vertex, from every vertex, these are called super vertices. This is a super vertex. Super vertex. They can be different. Here can be different graph from here. A, B, let's say. A can be different from B, yes? And then also you explode the edges. But you care, like when you explode this vertex, if you have here 3 edges, and this connector has to have also 3, and then connect one with other. Even you can do permutations here. So this is the idea. I explode every vertex, I explode every edge on a different way. And then suddenly I get, let's call it, this operation is called superposition, yes? Then suddenly I get huge snark, which is even hard to imagine, but you know what you're doing properly, it's okay. So I will talk like that, but I will not go into details. So usually these things, vertex is like this, or edge is like this. When I explode them, here is a cubic graph, vertices of degree 3, but I choose careful, and they are grouped. This is one connector, other connector, third connector for the vertex of degree, because our vertex of degree 3. And when you explode this, here will be also some cubic graph, but but here also we have, these are called half edges. So this is connector with 3 or more half edges, also here. The easiest way is to take here and here 3. The easiest way is to make super edge, if you don't want to be the trivial edge, which is also fine. Easiest way to take 2 vertices of Petersen graph, to cut it, and then you make a super edge. Let me illustrate this. So let's say we have, so I will need the tin. So we have the Petersen graph. Okay, I will cut it here and I will cut it here, let's say. So when I cut it, I mean by this. And this is one connector. Okay, and let's say I cut it here. I delete them. And this is the other connector. So this is a super edge. Easiest way to get super edge is to take snark and somehow to cut it some vertices. Yes, that's the easiest way. For the vertex is not so big problem. But anyway, you have to take a snark, then blow up all vertices, blow up all edges, and then you get a superposition of this snark, which will be again snark. This is the state of art. This is the most general construction. You can construct many different snarks this way, yes. This is something, so I'm not going into this. This is, you will get on the slides, so you can read it if you want. And this is the cohort. Even here in the slides are not in more general way presented. It's a little bit restricted, yes, not to be too, but it's still too much, yes, we didn't have time to. So this is this theorem, not of Coco, also of somebody else, of Fiume, I think it is. But Coco used this to make a snark with arbitrarily large girth. So this is it. This is what I wanted to tell. This is what I wanted to tell extra. Now we can have a look in the exercises. Dina, can you upload the exercise here?
Yeah.
Or maybe from laptop, or maybe from here, yes. So you can try. I don't know how we're going to solve now. We didn't print it so many copies. Some of people cannot.
Can we make them group of 4 or 5? So
They can make themselves, yes.
yeah. So that
I mean, I don't know now. You are alone. You can share, sit with somebody together, watch them, and you should group because these problems are not so easy anymore. No, some of them are. The first one is easy. I guess the first one is easy, yes? Anyway, we can demonstrate the first one. Good job.
yeah. So whatever first one, automatic index of
Complete graph.
K and observation. If you delta when n is even and n is 1 when n is equal.
Yeah.
Yeah. So whatever first one, automatic index of
Complete graph.
K and observation. If you delta when n is even and n is 1 when n is equal.
Yeah, yes, we can maybe explain that now.
I just use observation is case to do this. Try to prove that. Yeah. Try to prove that.
When n is equal, it is easy to partition the edges into both sides.
Sorry?
When n is equal, it is easy to partition the edges into both sides. When n is odd,
Yeah, you
and
try to
decomposition like
try to understand how you are going to do this. He will explain. I said, okay.
He saw something?
Yeah.
He saw everything.
So you want to keep.
He showed, there was like, he showed me some volunteers saw something.
Sorry.
He need for volunteers to present the. He showed it? He showed it. Okay.
Let him try to.
Yeah, okay. I know it's difficult because it's some new topic for you, and the question is not so easy.
So everybody, you are solving yourself, don't do that. You try to discuss it.
Yeah, it's sometimes important to work discussing together. This is even more important nowadays. So, yeah, something that this is the idea. So it's important because The hardest projection. That's all of the items. Should I solve one of these most largest component? Yes.
Sorry.
Should I solve exercise 12? Just ask of something. Because
This is related in them. This is easy. You want to solve something?
no, just to, for example, this one I know how to solve.
Let them do this.
12 is very easy. Exercise 12 is very easy.
Well, I said that I didn't.
So, who gave most starts from Colombia? That's very easy. If it's California, maybe you can finish early. Think of that. How good.
Okay.
That's easy. Think of that. You should solve 12 in 2 minutes.
Yes, we want to.
Which one?
First one.
First one, okay. In each group, the first one should be easy. Or easier. First.
Okay, I think we all have found this. So basically, if n is even, the edge chromatic number of the complete graph should be n minus 1, and if it is odd, then it will be actually of class 2, right? So this thing should happen. How I was thinking, like suppose for even case, say for example case 6. So first we will see how many edges can we assign the same color. Okay, so in case 6, if you see that we have 3 independent edges over here, right? 3 independent edges over here, and we can assign these edges the same color, and in the same manner, let me see. So again, these 3 edges are also independent. Okay, so we can assign them same color also. So that's why you can see, actually I remember a result that says that we can split the complete graph like this in edges independent. So it was starts or by what two factor theorem, I don't remember, but it was there. So basically so for K6 you can see how many edges are there, the number of edges. This will be 5 plus 4 plus 3, right? So that will be 5 into 6 by 2. So that is 5 into 3. Okay. So now you can see that for each group of 3 edges we can assign the same color. So how many colors will be required? Obviously 5. You can see, right, we can do the partition, we can do 5 such type of partitions of edges, independent edges. So 5 partitions there, and for each partition we will assign the same color, and in that way by using 5 colors we are done. Okay, so I think you all are convinced. And now for odd case the that thing is not sufficient, one extra color will be required. You can see.
So,
So,
you know to explain why it's not sufficient?
yes, sir.
Do you know how to explain why it's one more color needed?
Odd case. He
So
said
it-
that.
Okay, so next page. Okay. Now, if it say suppose for odd situation, let us assume case 7. So in the same manner we can do all even things. Now in case 7, what do we have? Let me draw. So again in this situation also the biggest group of independent edges what we can found is of size 3, right? So at most 3 edges you can assign the same color, right? And number of edges, what about the number of edges over here? That is 6 into 7 by 2. So that I think 21. So basically in this graph we have 21 edges, and if we are only allowed 6 colors, okay, so then what will happen? 6 times 3, 6 into 3, only 18 edges will be colored, and you know that we have the upper bound delta plus 1, so it must require 7 colors, right? So I think that.
So is it same as saying ki, when n is even, so we can find disjoint one factorization. How of it matches the same. Minus one
Yeah.
matches. Disjoint perfect matches. And in when n is odd, that time we cannot find perfect matching. Because all conditions will not be satisfied, and because of that, we will have to some edges.
Okay,
Thank you.
exercise 12 is very easy. Maybe exercise 12 is the easiest. 13 is also easy. You should use this dot product which I explained before to get the answer stance. But this term is a little bit work. Exercise 12 doesn't require too much work. It's easier we can solve.
Which is the need and
Do you want me to solve exercise now? Or somebody else can solve it?
let them.
It's very nice, it's very nice.
Yeah, now they were with exercise 1, so we let
No, it's
some
very
more
nice.
time. So easy is term is relative.
So it's very
It is a relative term.
and looking at exercise. It counts in its right as well.
Color 12 wala. Alright? See.
Saw something?
Getting this.
Which one?
Thank you.
Okay, I saw for you tell. But you want to go slowly. Because it's so beautiful. Should you saw for you 12? Okay, I saw for you tell. But you were very sorry. Sorry. Because it's so beautiful. She is so for you 12? This is the best exercise.